Welcome to the Dude Where's My Carat podcast, episode 7, Sapphires. I am so ridiculously excited for this one.
Oh, it is a brilliant topic. We are covering a lot of ground today.
We really are. But before we get into the heavy science of today's deep dive, I want you to do something for me. Just take a second and look down at the smartphone in your hand.
Or your smartwatch, if you're wearing one.
Right, exactly. Give that screen or maybe that little camera lens on the back a quick tap. Just a little tap.
Hopefully not too hard.
Yeah, please don't smash your phone. But it is highly likely that the crystal clear material protecting your device right now is the exact same substance that ancient Persian mythology believed was the literal foundation of the Earth.
It's quite a striking image, isn't it? The Persians basically hypothesized that the Earth rested on this giant cosmic gemstone.
A massive sapphire just holding up the world.
Yeah, and they thought the sky itself was just a reflection of its deep blue color.
I mean, it's a beautiful concept. Utterly wrong, structurally speaking, but beautiful.
Very wrong. But it sets up our mission for this deep dive perfectly.
Exactly, because today we are going to strip away the mythology and, the cheeky jewelry store marketing to look at what a sapphire actually is.
Because understanding how this single material bridges the gap between ancient folklore, royal engagement rings, and the microchips powering the device you're listening to us on right now, well, it requires looking at the actual chemistry.
Right. So, mineralogically speaking, a sapphire is just a variety of the mineral corundum.
Spot on. Corundum is simply crystallized aluminum oxide.
Which sounds incredibly dry and industrial.
It does. But to understand why it's so special, you have to look at its atomic structure. The oxygen atoms form this tightly packed hexagonal grid,
Okay.
and the aluminum atoms sit perfectly tucked into the tiny spaces between them. It's an incredible, dense, rigid lattice.
And that density is what gives it that famous durability, right? I mean, we know it's a 9 on the Mohs hardness scale.
Exactly. It's the third hardest mineral on Earth, right behind diamond and moissanite.
You're not going to scratch it with your car keys, basically.
Not a chance. But here is the fascinating bit. In its absolute purest, chemically perfect form, that aluminum oxide lattice is completely colorless.
Oh, wow. Really?
Yeah, it looks essentially like transparent glass, a white sapphire.
Okay, let's unpack this. Because if it starts out clear, how on earth does it transition from a boring, clear industrial crystal into the, vibrant blue gemstones we all recognize?
It all comes down to a process called atomic substitution. Think about it. While that corundum crystal is forming deep underground over millions of years, the surrounding geological environment is rarely perfectly clean.
Right. It's a messy place down there. Lots of dirt.
Lots of dirt, magma, metamorphic rock, and occasionally a stray atom of a transition metal like iron or titanium will just slip into the crystal lattice.
So it literally crashes the party and takes the place of an aluminum atom.
Precisely. It's a physical architectural swap within that highly structured grid.
Think of pure corundum as like a blank, colorless canvas. And these trace elements are the drops of paint.
That's a brilliant analogy, and that physical swap is what creates the color.
How does that actually work with the light, though?
Well, when an iron atom and a titanium atom substitute for aluminum right next to each other, they can actually pass an electron back and forth when light hits the stone.
Like a microscopic game of ping pong.
Exactly.
Yeah.
And that energy transfer absorbs the red and yellow wavelengths of visible light,
Leaving only the blue wavelengths to bounce back into our eyes. That is mad. That structural quirk is what gives us the classic velvety blue sapphire.
It is, and naturally, substituting different elements absorbs different wavelengths of light.
So what happens if you get, say, chromium in the mix instead of iron?
If the geological environment is rich in chromium, those atoms substitute into the lattice instead. But chromium atoms are slightly larger than aluminum atoms.
So they sort of bulge out.
Yeah, they physically distort the crystal field around them. And this specific distortion absorbs yellow-green light and reflects red and pink.
Wait, reflects red. Which introduces a completely hilarious semantic debate in the gemology world. Because if enough chromium gets trapped in that lattice, the stone stops reflecting pink and starts reflecting a deep, vivid red.
And at that point, we stop calling it a sapphire entirely.
We call it a ruby. It absolutely blew my mind when I read this in the sources. Rubies and sapphires are chemically the exact same mineral.
Structurally identical. The line between a dark pink sapphire and a light ruby is entirely dictated by the parts per million concentration of chromium.
which sounds like a nightmare to regulate.
Oh, gemologists argue over it constantly. It is a highly subjective boundary.
Let me guess, because the word ruby carries a massive financial premium.
You've hit the nail on the head. Calling it a ruby instantly inflates the price.
That is so cheeky. Okay, while the ruby and the blue sapphire get most of the historical glory, the absolute crown jewel of fancy colored sapphires is something else entirely.
Oh, you're talking about the Padparadscha.
Yes, the Padparadscha, it's a Sinhalese word, right? Meaning lotus blossom.
That's right, and it refers to this incredibly rare, highly specific color combination of pink and orange.
Like a tropical sunset. Or maybe the flesh of a really fancy wild salmon.
Wild salmon is a great way to picture it. But what's fascinating here is how strictly the industry guards that specific color.
Because to get that hue, the Earth has to provide this highly improbable freak of nature balance of both iron and chromium at the exact same time.
Exactly. The Laboratory Manual Harmonization Committee, the LMHC, has set incredibly rigid parameters for it. The color must be a subtle, continuous mixture.
No blotches allowed.
No blotches. And if the tone is even slightly too dark, or if the saturation crosses a very specific threshold of intensity,
Oof, it loses the title.
instantly it reverts back to being just a standard orange or pink sapphire.
And the astronomical price tag plummets.
Oh, massively. True Padparadschas can easily fetch well over $30,000 per carat. They frequently surpass the finest blue sapphires.
It's a strange paradox, though. We place immense financial value on these static, perfect colors. But the Earth itself is anything but static.
Right, it's a dynamic system.
Over the tens of millions of years it takes for these crystals to grow underground, the surrounding chemistry is bound to change, surely.
It does all the time, which is how we get party sapphires.
I love these. Explain how they form.
Well, a crystal might begin its growth cycle in an iron-rich pocket, right? So it starts forming a yellow core.
Makes sense.
But geological events, tectonic shifts, magma intrusions, that sort of thing, can drastically alter the chemical environment.
So a sudden wave of titanium might just wash over the crystal.
Precisely. And that causes the outer layers to suddenly start growing in blue.
So you end up with a single, continuous atomic grid that is visibly striped with distinct color zones.
It is literally a geological core sample, a snapshot of the Earth's changing chemistry frozen in time.
That is so cool. But here's the problem. There's a fundamental ceiling to relying on natural sapphires.
Right. A very hard ceiling.
You cannot build a global electronic supply chain or even sustain a massive commercial jewelry market on stones that require millions of years and hyper-specific geological accidents to form.
You really can. Take the legendary Kashmir mines, for example.
Oh, the velvety blue ones.
Right. They were prized for having microscopic titanium dioxide needles called rutile silk that scattered the light and made the stones seemingly glow.
They are gorgeous.
They are, but those mines were practically exhausted by the late 1880s. The natural supply is finite.
So industry needed a shortcut. I mean, if a sapphire is ultimately just aluminum oxide with a few architectural swaps of trace elements, the obvious next step was asking, can we just bake our own?
And we did. The first successful commercial attempt was in 1902.
By a French chemist named Auguste Verneuil.
Yes, he invented a process called flame fusion.
Which sounds like a special attack in a video game.
It does sound quite dramatic, but the mechanics are relatively straightforward. You take highly purified aluminum oxide powder, and you literally drop it through a specialized torch.
A torch burning oxygen and hydrogen at over 2,000 degrees Celsius.
Right. The powder melts instantly into droplets, which fall onto a little ceramic pedestal below.
Like an incredibly dangerous stalagmite.
Exactly like that. As the pedestal is slowly lowered, the droplets crystallize, building up a synthetic, bottle-shaped crystal called a boule.
Okay, but I have a major pushback question here.
Go on.
If a lab-grown sapphire is chemically and physically identical, I mean, it's actual aluminum oxide, why on earth is the natural one worth tens of thousands of dollars more per carat? Are people basically just paying a massive premium for dirt and natural mistakes?
In a word, yes.
That is hilarious.
But you have to understand, in gemology, mistakes are the ultimate proof of the Earth's history. Natural stones have inclusions.
Like the rutile silk you mentioned earlier.
Exactly. Silk, little mineral fingerprints, angular color zoning, lab-grown stones, which are created in days rather than millions of years, are almost too perfect.
They lack character.
You could say that. Plus, the engineering has become vastly more sophisticated since 1902.
Right, the sources mention the Czochralski process, which seems to be the backbone of modern industrial sapphire production today.
The Czochralski or pulling method is fascinating because of the sheer scale of it. Instead of dropping powder through a flame, you melt high-purity alumina in an iridium crucible.
Which sounds incredibly expensive.
It is. Then you introduce a tiny, perfectly structured seed crystal of sapphire on the end of a rod, and you dip it just barely into the surface of the melt.
Because the molten alumina naturally wants to align with the existing crystalline structure of that seed.
Exactly right. As you slowly pull the rod upward while continuously rotating it, the molten material cools and crystallizes onto the seed.
So you're literally pulling a giant crystal out of a molten bath.
By painstakingly controlling the temperature and the pulling speed, you can grow massive, flawless, cylindrical boules of sapphire. We're talking crystals that weigh over 200 kilograms.
200 kilos of flawless sapphire. That's the size of a large man.
It is a massive piece of rock.
But wait. If the chemistry and the atomic lattice of that lab-grown stone are completely identical to a natural one, how do gemologists even spot a fake when they cut it up for jewelry?
They have to look for the physical signatures of artificial rapid growth.
Like anomalies from how fast it cooled.
You're on the right track. A natural sapphire forms in an underground rock cavity, right? So it develops straight, angular growth lines that mirror its natural hexagonal shape.
Makes sense.
But a Verneuil flame fusion sapphire grows in a rotating molten droplet. Under a microscope, you can often see curved growth lines known as striae.
Because it was spinning while it cooled.
Precisely. You might also spot tiny, perfectly spherical gas bubbles that got trapped when the powder melted too quickly for the gas to escape.
But there's also a highly specific chemical giveaway involving ultraviolet light, isn't there?
Yes, this is a very clever test. If you take a natural, completely colorless white sapphire and expose it to shortwave UV light, it usually blocks the radiation. It appears totally opaque. But a synthetic, colorless sapphire lets the UV light pass right through.
But why? I mean, why does a supposedly identical material react so differently to radiation?
It comes back to the messy reality of nature versus the sterile lab. Even in a visually colorless natural sapphire, there are usually often up to 1700 degrees Celsius.
You can fundamentally alter its appearance. You are essentially just finishing the oven baking process the Earth started, but ran out of time for.
That is precisely what it is. At those extreme temperatures, the rutile silk actually dissolves back into the corundum lattice,
Which clears up the cloudiness.
vastly improves the clarity. And furthermore, if you carefully control the oxygen levels in the heating furnace, you can force the iron and titanium atoms within the lattice to interact more efficiently.
Dramatically intensifying that blue color.
Exactly.
Which perfectly explains why an unheated natural sapphire, one that emerged from the dirt with perfect clarity and vivid color without any human baking, commands such an insane price. It's a statistical anomaly.
It truly is. But if we connect this to the bigger picture, the true revolution wasn't in making affordable jewelry.
No, not at all.
The realization that we could use the Czochralski process to mass-produce massive, flawless, super hard sapphire crystals that fundamentally shifted the material from a decorative luxury to a strategic industrial necessity.
And the numbers back that up. Current market analysis projects the global sapphire technology market will reach $14.2 billion by 2030.
That is a staggering figure.
Here's where it gets really interesting. A $14 billion market is not being driven by engagement rings. It's being driven by the physical properties of the lattice itself.
Right, because we know it's incredibly hard.
But it also boasts a melting point of 2040 degrees Celsius. It possesses high thermal conductivity, and crucially, it is optically transparent across a massive spectrum of light.
From deep ultraviolet all the way through visible light to mid-infrared.
Those traits make it an absolute super material for harsh environments.
Completely. If you expose conventional glass or most plastics to extreme heat, corrosive chemicals, or high pressure, they degrade, melt, or just shatter.
But sapphire remains perfectly inert and optically clear.
And the single biggest catalyst for that massive market valuation is the device you, the listener, are likely looking at right now, LEDs.
Okay, if you're wondering how a gemstone makes a light bulb or a television screen work, it comes down to semiconductor manufacturing, right?
It does. To make a high-efficiency blue or white LED, you have to grow a microscopic layer of a semiconductor material called gallium nitride.
Gallium, short.
Right. But you cannot just grow gallium nitride in thin air. It requires a highly stable structural foundation to grow upon.
A substrate.
Yes. This process is called epitaxy. The crystalline structure of the foundation must closely align with the structure of the gallium nitride so the atoms can bond properly layer by layer.
It's like a microscopic architectural blueprint.
Exactly. Gallium nitride has a hexagonal crystal lattice, and as we discussed, sapphire also has a hexagonal lattice.
So they match up.
While the alignment isn't mathematically perfect, it is close enough to facilitate the growth. But more importantly, the process of depositing gallium nitride involves extreme heat and highly corrosive precursor gases.
Oh, and because sapphire doesn't melt until past 2,000 degrees and doesn't react with the corrosive gases, it survives the manufacturing oven perfectly intact.
It does. Nearly every high-brightness LED in the world, including the backlight illuminating the screen of your smartphone, relies on a microscopic wafer of synthetic sapphire as its foundation.
That is wild. And if you're wondering why your phone doesn't just overheat and melt its own screen while you're watching a high-definition video, the thermal conductivity of that sapphire substrate is a major part of the answer.
It efficiently draws the heat away from the semiconductor.
We also leverage its mechanical durability on the outside of our technology too, don't we?
Oh, absolutely. The barcode scanners you encounter at the supermarket utilize sapphire glass to prevent the laser window from becoming scratched by thousands of products dragging across it.
High-end watchmakers use it for the crystal faces. Rolex, for example.
Yes, and Apple uses it to protect the camera lenses on their smartphones, ensuring that the steel of the keys in your pocket, which sits much lower on the Mohs scale, cannot scratch the optics.
It's remarkably ubiquitous, but the aerospace and defense applications are where the physical limits of this material are truly tested.
Consider the engineering challenge of a supersonic missile, an advanced drone, or an orbital satellite.
Okay.
These systems rely heavily on optical sensors and infrared cameras to navigate and track targets.
But you obviously cannot leave delicate optical equipment exposed to the environment at Mach 3.
Exactly. The aerodynamic friction alone at supersonic speeds generates blistering, intense heat. Combine that with airborne dust, ice, or rain hitting the craft at hundreds of meters per second.
Conventional glass windows would just shatter or melt instantly. Plastics would vaporize.
But synthetic sapphire survives. Manufacturers machine these massive lab-grown boules into aerodynamic domes that cover the noses of supersonic aircraft and missiles.
And the sapphire withstands the extreme atmospheric pressure, the thermal shock, and the kinetic force of supersonic flight.
All while remaining perfectly transparent to infrared wavelengths, so the sensors inside can continue to see perfectly.
It's also used for transparent armor in military vehicles.
Right.
And viewing windows in extreme high-pressure scientific equipment.
Like deep-sea submersibles or vacuum chambers?
Yes. It is a profound juxtaposition when you really step back and look at it.
What do you mean?
Well, the exact same corundum lattice sitting in Princess Diana's iconic engagement ring, the one Kate Middleton wears today, is structurally identical to the material serving as an invisible, indestructible shield on a supersonic missile.
That is a mad thought, isn't it?
It's the same architectural grid making up the tiny glowing LED inside your television remote.
It is a testament to the incredible versatility of aluminum oxide. I mean, nature spent millions of years utilizing this rigid lattice to capture ambient trace elements, inadvertently building these beautiful, highly flawed masterpieces of color.
And then human engineering took that exact same structural blueprint, perfected the chemistry, removed the geological flaws, and used it to physically build the backbone of the modern information age. We've covered an immense amount of ground today.
We really have.
We started with ancient Persian mythology, where a cosmic gemstone painted the sky blue.
We unpacked the rigid atomic structure of corundum and the physics of how a misplaced chromium atom can turn a clear crystal into a ruby.
Or how a highly specific balance of elements can create the astronomically expensive Padparadscha.
We examine the limitations of natural supply that drove Auguste Vernoy to invent flame fusion.
And how the modern Czochralski process pulls massive, flawless boules from molten alumina. We looked at the intricate detective work required to separate a million-year-old geological artifact from a crystal baked in a lab last Tuesday.
Relying on UV absorption and curved stria.
And finally, we explored how the thermal and optical properties of those synthetic crystals completely disrupted modern engineering.
Creating a multi-billion-dollar industry that enables everything from semiconductor epitaxy to aerospace defense.
So what does this all mean?
Well, it leaves us with a rather provocative question about the future of value in human perception.
Lay it on us.
As our manufacturing technology continues to advance, as we refine our ability to create chemically flawless, physically indestructible synthetic materials at massive scale, for a fraction of the cost, what ultimately happens to our definition of luxury?
It forces a massive reevaluation of what we are actually paying for.
Exactly. Will future generations continue to place astronomical monetary value on imperfect natural stones simply because they possess a geographic passport?
Right. Will we always pay a premium for a stone simply because it is a finite, flawed relic of the Earth's chaotic history?
Or will the fundamental concept of luxury eventually pivot? Will we eventually come to champion absolute, unyielding technological perfection over natural rarity?
I mean, when a lab-grown Padparadscha is visually indistinguishable and structurally superior to a mined one, what does it actually mean to own the real thing?
It's a fascinating structural and philosophical puzzle to leave you with.
It really is. Thank you for joining us on this deep dive into the hidden world of sapphires. We hope this exploration has given you a new appreciation for the materials operating quietly in the background of our lives.
Absolutely. Cheers for listening.
Stay curious, and the next time you tap your phone screen or